So previously we've talked about momentum. We talked about inertia, and we talked about momentum in another section. In that same section, we were throwing inertia and momentum into the same topic. When talking about energy, we want to kind of relate energy and momentum to each other. Both of them have conservation laws, as a matter of fact. Momentum's conservation law is a conservation law. In no way, shape, or form can you ever violate the conservation of momentum. The only way we can, in a sense, is by introducing an outside force. That just simply means that we haven't looked at the universe big enough. A lot of people say, hey, look, I can throw a ball and I'm violating the conservation of momentum because the ball is not moving and now the ball is moving. You're actually not violating the conservation of momentum. You're just not considering all of them. I mean, the example of taking something and throwing it up would seem to be a violation of the conservation of momentum. It's not, because the momentum of this ball going up, or this pin going up, is actually equal to is equal and magnitude of the Earth's momentum going down. It all equals out. It's just you have to make your system big enough. But anyway, and then energy has a conservation law. This work energy theorem, where when you throw in potential and kinetic, you equal total. And if you have non-conservative forces like friction in there, you can say potential total, or potential kinetic, and non-conservative energies equals total. Sometimes it's not so easy to determine what other work is going on in the system. A perfect example of that, or two perfect examples of that, are collisions and explosions. They're both basically the same thing. So that whenever you're experiencing a collision, okay, when two cars are colliding with each other, it's very difficult to be able to keep track of all the non-conservative forces in the system. You had kinetic energy, you collide, you don't have kinetic energy. Okay, that energy goes in a whole bunch of different forms. Sound itself is a form of energy. Heat, the temperature change of the material, is an energy. There's even stored energy in the deformation. Twisting a frame is energy. Okay, so that's all there, but we don't really say, all right, there's 2.7 joules that have gone into sound. There's 27.5 joules that have gone. We just can't do that. So when we talk about collisions and we talk about explosions, we need a different way of talking about it. So what we do is we come up with these two brand new concepts. We come up with the idea of inelastic and elastic collisions. So when we talk about momentum and we talk about energy, we're talking about either one of these two ideas: inelastic, elastic, and elastic. And it turns out that an explosion is in there too, but it's inelastic. Okay, and all that means is when we're referring to things as inelastic and elastic, this means that energy is not conserved, and there's my abbreviation for conserved. And in an elastic collision, energy is conserved. Okay? So in an inelastic collision, energy is not conserved. All that means is that there's energy that we can't keep track of. I mean, it's technically conserved, but you just can't keep track of it. There's really no physical way of doing that. In elastic collisions, energy is conserved. An example of a near elastic collision, it's very difficult to get a really elastic collision, with the exception of maybe on the atomic scale, is billiard balls. When billiard balls are hitting other billiard balls, they're relatively elastic collisions. Now, they're not perfectly elastic because there is energy that's being transferred from one billiard ball to another. The billiard balls heat up when there's a collision. So there is energy that isn't necessarily conserved. In addition, sound, every time there's a collision with another billiard ball, you hear it. That sound is energy, and you're not keeping track of it. So there are very few really elastic collisions, but we like to say near elastic, okay, or even to take it to the point, there are very few perfectly elastic collisions. But for the most part, we'll just consider some collisions to be elastic, simply because the energy losses of those systems are pretty small. In the case of the billiard ball, there's very little energy that's turned into temperature change, and there's very, very little energy in sound itself. Sound doesn't carry a lot of energy with it. So elastic collisions are something where energy is conserved, or in the case of nearly perfect elastic collisions, energy is conserved except for a little bit. Okay, when you talk about atoms slamming into atoms, well, they're not actually slamming, they go womp like that. They don't necessarily hit each other. Those are elastic collisions. Those energies are conserved. Inelastics are systems where energy is not conserved. And typically when you experience inelastic collisions, the two objects are either binding with themselves. You have a car that collides with another car. They're bounded. They're interwoven with each other. So both cars are moving together. Okay? That's a result of what we call deformation. Energy, you can spend energy to deform an object, so that's called deformation. Or in the case of an explosion, if you think about an explosion, you got yourself a mine sitting there, or a shell sitting there, and it's not doing anything. It doesn't really have potential energy. It has chemical potential, but it's something we don't keep track of. So it looks like it has no energy, then all of a sudden, bam, it explodes and has all this kinetic energy. So in that way, it's not really being conserved because we never really took into account all the chemical energy that's inside that object. Okay, so that's the difference between an elastic and an inelastic. The inelastic energy is not conserved. An elastic energy is conserved. Now, why would we do this? I mean, we were talking about energy as being simplifying our emotions. Well, collisions are terribly complicated. Are terribly complicated motions. Collisions and explosions, I should say. I should put that in there. So we need every tool we can get in order to understand them. So when we introduce these inelastic and these elastic collisions, we're introducing energy into the system, which is these scalar numbers, but we're also introducing momentum into the system, where the momentum gives us these vector quantities. It keeps track of direction. So it gives us more tools to work with in order to solve these problems. I should also add, because conservation of momentum is always conserved. P is conserved. So that means that either in either case, an inelastic or an elastic collision, that momentum is conserved. Okay? So that's another way of talking about problems. That's another way of talking about motion. We couldn't talk about collisions and explosions in kinematics. We can't even talk about them in forces. It's just not practical. Those are non-constant forces. Those accelerations are going all over the place in a collision. So very, 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 very few people are going to waste their time talking about every single forces that happen, especially in a complex thing like an automobile collision. Okay?